All right, good afternoon, everyone. Any questions before I get going? Okay. So today we're going to have a lecture on a bunch of Scala background that we need before we can go forward with building parsers and code generators. So this is somewhat technical material about Scala, but I'll try to put it in a background that's befitting to a programming languages class. So first of all, Scala is probably the first mainstream programming language that tried to put together both functional and object-oriented programming. And if you think about it, that at first glance seems like an odd thing to do, because when object orientation first came into the mainstream, people said, what does object-oriented programming mean? What are objects? An object was defined as something that has three characteristics: state, behavior, and identity. And from a functional point of view, two of those don't make a lot of sense. So state implies that you can change the state, that you have mutable state, and mutation is not something that we see in a functional program. Identity also doesn't make a lot of sense. In a functional program, if you have two quantities that are the same, let's say you have one list that contains 1, 2, and 3, and you have another list that also contains 1, 2, and 3, we don't really care whether they're identical or whether they're two distinct objects with the same contents. All we care about is equality. But still, there are great advantages to object-oriented programming. It gives us a way of clustering responsibilities. And so what Tversky, the creator of Scala, said is that we don't want to forego those benefits. There's no need that state has to be mutable. You can make classes and that are immutable, and they make perfect sense in a functional setting. And by kind of hiding the possibility of checking for object identity, and by making it easy to check for object equality, we can really use objects to make functional programming more expressive. And so that's what he did. So actually, Scala is not a very opinionated language. You can perfectly well do everything that you can do in Java and Scala. So you can have objects with mutable state. We're just not going to cover in this course. But as a general Scala programmer, of course, many times I do use mutable objects. Right now, we're just going to restrict ourselves to the functional setting, as we have for the last several weeks. So here I give an example of a class, a class that represents a point with an x and a y coordinate, the way that you might write it in Scala. So we say class point, and now notice that we have right here something that awfully looks like a constructor definition. For a good reason, because it is a constructor definition. So Scala has a very compact notation where you put the definition of the class and the definition of the constructor right with each other, so to speak. So the point class defines a constructor where we construct a point with an x and a y coordinate. The word val here means that, first of all, of course, means that the x and y coordinates are immutable, but it also means that we will get accessors for free. And that's nice, so we don't have to do what we had to do in Java, where you have to define a getter, and for x and y, the getter is absolutely free. The way you call the getter is if you have a point, you just say p.x. It's that's just a getter. You can't say p.x equals, but you get the value. Oh, yes.
So just to clarify, the val is what lets us access x like that?
Yes.
Okay.
Yeah. We'll see later what happens if you omit the val. That also gives us something. But if you think of the boring classes that you write all the time, they will have a constructor that initializes all of the fields, and it'll have a getter for each of the fields. And so this very compact notation gives you exactly that. And in this course, it turns out that's what most of our classes will look like. Now, that means that these constructor parameters, they end up being essentially public, right? We have getters for them. And so you might say, from an object-oriented point of view, that is really terrible because we don't have encapsulation. And I have an answer to that. And the answer is yes. So in our situation, we don't care about encapsulation. We're not building programs that need to withstand 10,000 years of evolution. And if we do, Scala does give us tools to manage that. But in most of the situations, if you have a point, it's not going to magically look different 10,000 years from now. It's going to have an x and a y coordinate, and all of that stuff with having to do the getters and all that is just unnecessary pain. So Scala actually makes it easy to do the things that you do all the time, and it makes it possible to do some of the other things as well. All right, moving on with this class here. So inside the definition of the class, you see the definition of the methods, just like you would do in Java, and they look pretty similar. So here we have a move method that moves this point. It takes the distance as parameters, and then this is a simple method with just one result. So we have the equal, and then it returns the result. So just like with the other methods that you've seen, there's an equal, or by the functions that you've seen, there's an equal, and then the result of that function. Of course, the move method cannot mutate this point. It's immutable. It returns a new point with the coordinates after the movement. Exactly like what we've seen so far when you add to a list or when you add to a map. You get a new object out that has the changed state. Here is a method that doesn't take any parameters, and because of that, we don't put any parentheses in here. That's the Scala convention. And otherwise, just computes an answer. Here, this massive square. The toString method works just like in Java. In fact, every class in Scala does extend java.lang.object, and so it automatically inherits toString, hash code, wait and notify, and so on. So when we define toString, we just, again, no parentheses because we have no arguments, and we just produce a string. The only difference is in Scala, when you override a method, you have to say override, so that way the compiler can check that you don't accidentally override or accidentally fail to override when that was your intention. So that part is not particularly difficult. So notice that there are 5 methods, the 3 methods that we defined, plus the 2 accessors that are implicitly given by the val constructor parameters. Now a bit more to constructor parameters. So like I said, whenever you have a val, then you get a construction parameter, a field, and an accessor to that field. If you omit the val, then you still get a construction parameter, and you get a field, but that field is now private to the class. You cannot access it. And that may be useful. So here I have a situation, maybe a little bit contrived, where I have a Scala random number generator that's constructed from a Java random number generator. And then the methods, the Scala methods, can still reference the construction parameter. So obviously, because the methods can be called long after construction, the class needs to stash away that reference somewhere as an instance variable. But the outside world, when having an instance of that, cannot access the interior. So in this case here, the val just drops the fact that this is public. So this is then actually some form of encapsulation. You can go further with encapsulation if you need to. You can declare a private val, and that way it wasn't there. The construction parameter is just like a private instance variable in Java. Notice, by the way, that inside the class you can have any code at all. So you have initializing the private val, because everything in here that's not a def is a part of the constructor. I'll come back to that in another slide. Finally, when you want to call the superclass constructor, so let's first make a subclass where we have that need. So you have a class labeled point that extends point. So a labeled point is an xy together with some label. Then you want to, in the subclass constructor, pass certain parameters to the superclass. So the label point gets 3 construction parameters, the x and y location, and the label. It then wants to pass x and y to the superclass, and the syntax is very compact here, where we just stick the x and y right in here. And it looks a little weird, because from a Java perspective, we're used to seeing class label point extend point, and now we have to kind of look past, at first glance, you have to look past the thing with the construction parameters, but it's okay, you get used to it. So it's a little odd that they interleave them like that. Notice also that these x and y do not have a val, because we do not want to have an extra accessor. We only want the accessor that already exists from point, which did have a val, so we therefore get x and y accessors. And if you have tried to have them twice, then it would say you have to use override or whatever. That's not at all what we want. We just want to have the same x and y accessor. Whereas the label does have a val because we want to be able to get at the label later. Now, it's actually perfectly legitimate when you're in your own code to always omit the val, and maybe there's no other customer who ever wants to access it, and that'll be fine too. Now, in Java, we have regular methods and we have static methods. And in Scala, they felt that static stuff, that's kind of weird. And so they take a different point of view from that. They say that sometimes you have a class where you only want to have one instance of the class. And they call that such a thing an object. There's several obvious examples of that. Sometimes you have some kind of a singleton. Like it might make sense to say you really only want one random number generator. There's no sense in creating 20 competing random number generators. A single sequence of randomness should be good enough. So you might want to make an object random that really means it's a class with only a single instance. The other example that you have in every program is when the program starts, really the application itself should be an object with a single instance. And that's how it works in Scala, in fact. You give the object a name, like main. I generally use main. Well, there's no reason not to. And then you have it extend the app object, which has generic things like capturing command line arguments. And then inside the constructor for the main object, you put in whatever the code of your application is, whatever you need to kick off the application. It's the same thing that in Java you would put into public static void main. And if you think about it, public static void main is kind of a bizarre thing. The Java launcher had to be specially rigged to recognize, to look for a class that has a public static void main. And in Scala, that's just not the way they do it. They say, we will just look for an object that extends the app trait instead. And that's the one of which we will make a single instance. And by making a single instance means we run the constructor. And that kicks off your application. So of course, as soon as main is constructed, your program ends. Unless there's some other threads that keep it alive. But certainly the main thread ends when main has been constructed. Yeah?
So we can view object classes as very similar to public static void main.
Well, yeah, and so you could think of something that's an object is like a class where all the methods are static. If the object extends app, then you can think of the constructor as the equivalent of public static void main.
Okay, got it.
Now, sometimes you just want to have a nice home for static methods. A static method's one that doesn't have a receiver. And the way you do that in Scala is when you have a class that has objects in it, and then you also want to have static methods, you make what's called a companion object for them. So for example, there's a list class, and there's also a list object. The easiest way to show that is to just look at Scala doc. So we'll look for list. Here it is. So here you have the familiar list class with its 300 some methods. And you can see up here the C means it's a class. When I click on the C, then I get an O. That's the companion object. And it has just a handful of static methods that I don't actually happen to know very much. So as it turns out, there's a concat static method that lets you concatenate any collection of lists, whatever. This particular class, the companion object, is not super useful. As one that I'll use a lot, there's a class called source, and it has a static factory method from URL where I can build a source by giving a URL string. So in Java, you have static methods. In Scala, you have these methods that are put in a companion object, and therefore they are essentially static. Yeah.
What would the declaration of a companion object look like? Would it be companion object extends list?
No, you have a class list, and then you have an object list.
Okay.
And they have to be, and I can't remember this, they have to be in the same file or the same directory or in the same place in some way that they really are companion. Maybe it's the same package. I'd have to actually look it up. I always put them in the same file. That's certainly good enough. So that Scala recognizes them as companions. So Scala has a specific notion of them, and you declare one as a class, the other with an object with the exact same name. So there's a trivia fact. In Java, you have a math class with a bunch of static methods. And in Scala, you may have noticed that we had the ceiling method on one of the slides several weeks ago, and it was inside a thing, lowercase math. That turns out not to be, that's one of the few exceptions, that turns out not to be an object. It's the math package. In Scala, you can put functions in a package as well as in a class, or an object. Now there's a special kind of classes that are optimized for pattern matching. We're going to see pattern matching on the next slide. They're called case classes. So right now you can think of a case class as a class that gives you even more shortcut notation as the regular class notation already gives. So with a case class, you first say it's a case class. You give a class name. And then whenever you put these field names of the constructor in there, then they automatically have a val in front of them. Or you don't have to write the val. You automatically get accesses for them. That's benefit number one. Benefit number two is when you construct an instance, you don't have to say new. So let's work through that with an example. Here I have a typical example. I want to have a very simple kind of tree structure. And I say there's two kinds of simple trees. The simple tree could be a leaf that holds an integer value, or it could be a node where the left and the right child are simple trees. So here the nodes don't have values, not like the trees that you saw in CS2. But I could easily also put interior values in here by adding another value in here. But so this is just a tree whose leaves carry values. Now, let me construct one of these. So here you go. So I have a leaf of 3 and a leaf of 2. I put them in a node. Then I put those in another node with these things here. And notice I didn't have to say new anyway. So it's actually somewhat a natural and useful thing not to have to say new. And that's one of the benefits that you get from case classes. If this had not been a case class, would have been a new node, new leaf, and so on. Or would have been just more baggage. The other thing is if I have one of these instances, and say I have a leaf and I want to know what its value, then I can say my leaf.value, and I didn't even have to put a val in here. So with the case class, the understanding is all of the parameters are automatically immutable, and they're automatically visible with these accesses. It turns out that those are very sensible defaults. There's another trick that case classes can do that we'll see on the next slide. So there's this general purpose pattern matching concept in Scala. There are many different instantiations of it. We're going to look at the one that's most useful to us here. So the match statement takes an expression, and it's then followed by a set of cases in braces. So each case has a pattern, an arrow, and then the expression that that is the result if the pattern matches. There's lots and lots of different variations of this. So let's look at the one that we're really interested in. So I have a tree, and what can a tree be? A tree is either a node or it's a leaf. And here's how it then looks like. You say you match. It's either a node or it's a leaf. And then inside the node, we say it's a node that was at one point constructed with the left and the right subtree. And we'll put the L and R in here. We say, or it's a leaf that at one point was constructed with a V. Yes?
Do you get a compiler if you don't have all the cases in the match statement?
There is a way of making you to get a compiler error, but we're not getting into that wrinkle.
Okay.
That's actually a nice feature. You can seal the class,
Yeah.
and then it's an exhaustive list.
Okay.
So the variables here are useful in practice because they let you access the interior structure of these objects. So let's look at a typical example. We want to sum up the values of all of the leaves. In this case, I write a function sum that takes a simple tree and it returns an integer. It's a recursive function, so I must give a return type. And as before, there's only two kinds of simple trees. It's a node or a leaf. If it's a node, then I recursively compute the sum of the left and the right. If it's a leaf, well, then the value is itself. And notice how the variable v, I didn't have to define it. I didn't have to give it any name. I didn't have to extract it out of the object. I just say this is a leaf of v, and then v was put in scope, and it is the value with which this leaf was constructed. Again here, L and R are the left and the right subtree with which this node was constructed. So it's a super compact notation. And that notation is only possible with case classes. There's some magic that goes on inside where, of course, T is some kind of an object. And then one needs to figure out what does it mean to be able to access L and R. And we're not going to get into the details of this, but the machinery that's required for doing this is a part of case classes. Now, matches are tried in order. In this case, it doesn't really matter. There'll be some situations where it may matter, and as soon as one of the matches passes, then that's the value. If you need to have like a default thing, then you would use a case underscore, and that matches anything. And of course, in that case, you still have access to the surrounding expression, but you don't know what it is. Yes?
Can you technically have two cases with the same name but different parameters?
So let's say if you had a case node LR, and then you had another case node XY, the second one would never be executed.
Oh, I see.
Because the first one matches, it is a node, and then L and R are bound to the left and the right subtree of the node. And the second one, in this particular case, you might even get an error message from the compiler that it's clearly unreachable. But the semantics is the first one that grips is going to be the one where it's executed. And then L and R are bound to the values with which the node was constructed. So clearly, you wouldn't put a case underscore as the first case, for example, because it would always match. And again, one would then expect a compiler error message. Now notice also that unlike the switch statement in C and C++ and Java, there's no break. You can never fall through from one case to the next. And that's, of course, good, right? When is the last time anyone in this room used break? No, I didn't use break. When is the last time you had a switch where you actually wanted to fall through? So I see one hand here of someone who did this.
If you have multiple cases, that should have one line.
Yeah, but that's kind of a degenerate thing, right? Where we have case A, case B, case C, and they're all. But in that case, you should be able to just write case A or B or C in a more sensibly defined language.
Oh, yeah, it's like a case.
Yeah.
Case. Just like three.
But every once in a while, you see some code where you want to do some action and then also fall to the next one. It's like super rare. And there's people research large bodies of code to see how often this actually happens. There's one well-known study where they looked at like the entire C++ compiler from Sun Microsystems years ago, and like in 99.4% of the cases, there was no fall-through desired. But in a good number of cases, the fall-through happened anyway because the programmer had forgotten the break. And so it's an exceedingly common case to forget the break. So that's an example of like a real misdesign in language design. Yes?
C# doesn't let you do it. It forces you to use break.
Oh, I see. Well, that's dumb too, right?
Yeah.
I mean, if it forces you to put in, something
For
like
that
that,
reason, though.
they should have just said there isn't no fall through.
Well, you can, as long as there's nothing on the next line, as long as there's no like action. Okay, so you could have the case A, case B, and then
I see.
You're
Yeah.
allowed.
Yeah. So basically, they also say that cases should be disjoint, and they really should be. Right. So in Scala, you don't have to say anything particular. The cases are disjoint, and that's the normal thing. All right, that's pattern matching. So we're going to be putting that to work with syntax trees. So now we're going to go back more to programming language parsing. If you have an expression, something that has a value, then usually that expression is made up of sub-expressions in some form. So these arithmetic expressions are a case in point. So you have an arithmetic expression, 3 plus 4 times x, and you can represent it as a tree. The times binds more strongly, so we have a subtree that multiplies 4 and x, and then we have a tree that combines the result of that by adding 3 as well. So that's the tree. Now we want to model this with a bunch of Scala classes. We have a superclass expression. We have a subclass number for these numbers, a subclass variable for the variables, and a subclass for operators. These are all binary operators. Each operator combines 2 sub-expressions that are the left and the right child. And the way the combining is done is described by a function. So here I'm combining them with multiplication. On the top, I combine them with addition. Now, we can very compactly generate this tree because we don't have to say new. This tree, it's an operator of the number 3 and another operator where in the end we combine the 2 by adding them. I'll do this in real time. And then there's another operator in the middle that is done in the same way, except it combines a number and a variable and it multiplies. Now at some point we want to be able to get this expression. Today we're not doing that, but on Wednesday you will see how to write a parser that takes the string 3 plus 4 times x and turns it into a tree like this. For today we'll take the tree as a given. Now we want to evaluate such a tree. We have to do a little bit of extra work here because when we evaluate a variable, we need to know what the value of that variable is. So we'll assume that someone has collected the variable values in a symbol table. That's just a map from the variable name to the value. And I'm not going to go over the map refresher here. I hope you still kind of remember how maps work. There's only one thing we need to know here anyway. So we're going to evaluate an expression with the aid of the symbol table. It's a recursive function, so we give an int return type. There's 3 possible expressions. An expression can be a number, a variable, or an operator. If it's a number, it evaluates to itself. If it is a variable, then the variable has a name, and we need to look up in the symbol table what is the value associated to that name. So recall that in Scala, when you have a map, you just use the functional notation to get at the associated value of the key. Now finally, if it's an operator has a left subtree, a right subtree, and a combining function. We now recursively call eval on the left and on the right. Notice that we need to pass the symbols map to those recursive evaluations. And then we get a value for the left subtree, a value for the right subtree, and then we pass them on to the combining function f, and that's the combined result. So that's all very simple, just a few lines of code. One thing to notice here is this eval function here is not a method of any class. We will later have to put it in a class, but you can just put it in main. So it's not an object-oriented approach. In an object-oriented approach, we would have made it so that each of these classes, number, variable, and operator, would have had its own eval. So the pattern matching is kind of the anti-object oriented. In object orientation, you take the point of view that each class is responsible for its behavior. So you might have eval as a method of expression. We look back on our class hierarchy. And each of these might then define its own eval method. That's an elegant way of doing it, but it's more complicated because now you have to define an abstract method and 3 concrete methods, whereas here we define everything in one place. It makes for more compact code. The object-oriented approach is good when you have an open-ended collection of potential implementing classes. Like if you think on the subclasses of some GUI widget, where they might come in all shapes and colors, then inheritance makes a lot of sense. If the collection is not open-ended, if there's only so many different subclasses, then it's usually much more compact to say, well, if it's this, do this; if it's that, do that; if it's that, do that. And so, in that kind of situation, this pattern matching approach makes a lot of sense. So you should think of pattern matching as kind of the functional analog to polymorphism that you have in object-oriented programming. And there's no one better or worse. Just as a practical matter, pattern matching works really nicely if the collection of subclasses is fixed, and polymorphism works great if this collection of subclasses is open-ended. All right, that's almost all I need to do. Before we get into the lab, the final thing I want to cover is functions with variable arguments, and that's for the homework. So one of the pieces of the new homework assignment is that you will re-implement homework 1. You must fondly remember homework 1. There's a Java homework to see that everyone was able to get into the class. And that Java homework was not chosen randomly. It's clearly something that we will need. It had to do with expressions and expression evaluation. And I'm going to make you recode it in Scala so that you can figure out how to use classes and case classes in Scala in a hopefully now familiar situation. But that Java homework used variable argument lists. And so I have to show you how to do that in Scala. So here I have a sample function that has variable arguments. You can call this sum function with, in this case, 4, in this case, 8 parameters. And in Java, okay, how would you define such a sum function in Java? So if you want to write a public static in sum, yeah?
You would just use a for loop.
Yeah, but how do you define the parameter type? You can't say int. If you say sum of int, then that's not going to work. Then you can't call it with some variable number of integers.
A double?
No.
Oh, the vargs?
How do you do the var args?
The dot.
Okay, yeah, okay, the dot, right? So you would have the dot to indicate var args. That works in Java and in JavaScript. Who's the C# expert in C? Okay, so maybe not in C#. But it's a common construct in many languages.
Wait, I'm sorry. You were asking. Oh, you wanted
the var args.
Oh, you're calling me out. Sorry.
Okay, so how do you do var args in C#?
Oh, var args. Params. Params. So it's like params, and then the type you want plus square brackets, like an array.
Oh, I see.
So it works as an array.
Oh, so there's a special kind of type for receiving var args.
The params.
Okay, good. So every language has its own syntax for that, and here's the Scala syntax, that you say it's an int asterisk. That means it's a sequence of integers, but it's somehow a special construct. They don't give you a particular class. Now, as you may see in a minute, that might have been a better idea, but this is how they did it. So what you get in args is you don't get an array like in Java. An array, if you say it's an int ... you get an array of integers. But instead you get something, and you don't know what it is, but it's of some class that implements seq of int. So you get a sequence. A seq is almost like a list. It has the same 350 or so methods. A list is a special case of a seq, and there's some minute difference. Yes?
Does Scala have something like keyword args, like in Python?
It does not have keyword args, but it does have args with defaults.
Oh, okay.
Okay, where was I? Okay, so you get a seq, and you can think of it as just like a list. And now you can work with that. So in this case here, I say to compute the sum, I just call reduce. Maybe I should have called fold so that it also works for an empty sequence, but I didn't. Now, that's all simple, and you don't have to think about it much. There's only one weird corner case, and that is sometimes it happens that you already have a sequence, and you want to pass it on to a method that wants a variable number of arguments. Now, when you do that, Scala is going to take the point of view that that's an argument and not a sequence. So if I should have put a call in the slide. If you want to call sum and then just pass a thing that's a seq, like 1 to 5, then by itself it's going to say, well, 1 to 5 is a range. That's a subclass of a seq. You can't pass a range to this function. It expects one or more integers. And then there needs to be a way of saying, hey, compiler, get on with the program. You're going to wrap this thing in a seq. Now, just don't wrap it. Take it as it is. And the way you do that is you put a colon underscore asterisk in there. So the underscore asterisk means it's a sequence, and the colon means, hey, just treat it as one, and then do the right thing. That syntax is not super elegant, and so it may well have been invented after the fact at some point, but it is what we've got. Now, why do you care? You care if you ever need to write a recursive function that takes variable arguments. Here I'm writing the sum function in a recursive fashion. So it's recursive sum. It takes a variable number of integers, returns an integer. Here I have the return type for the recursive function. And here's the base case, 0 if there's nothing in there. Otherwise, I have head and tail as always. And now when I call recursive function of args.tail, args.tail is the tail of a seq, so it's again a seq. Now that one, I have to now use that inscription here and say, let's take it and pass it on. In a sense, unpack it and repack it. Of course, it won't actually unpack it and repack it, it'll just pass it as it is. So anytime that you need to make a recursive function with variable arguments, that's the mumbo jumbo you have to go through. And that'll happen at least once in the next homework. So that's why I put that thing on there, so you can have it for the homework. Now, in the lab, I want you to do a couple of things. I want you to just make this evaluation tree, copy and paste the various methods that are required, and carry out the evaluation. And that really is so that you practice setting up an object main that extends app. And I want you to run it as an app. So don't use a Scala worksheet. Really make a new Scala project in the way that you normally make Scala projects. And either with the IDE or by running SPT. And then just put the code in there. You'll see when you put in the code, you have a choice where to put the classes. You can put them outside your main object, or you could put them inside. It doesn't really matter for this exercise, but in preparation for the homework, put them outside, because later I would like them outside, so it's a little bit easier for me to test them. And then I want you to write another method that deals with defining variables and setting up the symbol table for them. So in the mini language that we will build, we will have statements val x equals expression for defining variable values. And the way they need to be interpreted is, of course, by first of all, evaluating the right-hand side expression, and then by adding another key value pair into a map. Well, we can't add something to a map in Scala, so we have to make it so that we pass in a map and get out a better map. So I want you to write that function that does that, and that's another function called eval that processes a definition and an incoming map and produces the augmented map. I also call that function eval. It's not quite the same as the other eval function, but that's fine. You can overload method names in Scala just like in Java. So go ahead and do that, and then I'll do some live coding in the end of like in 20 minutes or so that we're all on the same page for the homework. Oh, and talking about the homework, one thing, you all got the homework back, and there were a number of people who got 0 points on it, probably for no particular reason other than some incompatibility between the tester and the way you've packaged that. So I put a post on Piazza. If you are one of those unhappy people, please fix up whatever it might take, resubmit it, send me an email, and I'll regrade it. Yes. I did post the answers for homework 4 like a week ago when I left town. So you should look for that on Piazza, and if you can't find it, put another post. Yes.
Could you also share the test suites?
I believe I did.
Oh, you did?
I meant to share the test suite, so I always mean to do that. So look into the whatever the test subdirectory, and if they're not in there, then let me know. Then I would have messed up. But I must have, because all I gave the grader was the link to that homework.
Okay.
Yes.
I didn't have that incompatibility thing for, but that was for homework 3, and I didn't email you about that. Like, I think exactly the grades came out. So how
Yes.
do I know if that?
Oh, you. So I believe I'm up to date with all of the previous regrade reports. So look into your repo, and if that file has been updated, then you know I did that. And if not, send me another email. So I mean, it usually takes me a week or so to catch up, but I think I'm caught up. Yeah. The other thing is, there's a very real possibility in this test that it just didn't compile if you didn't get all the way through to the last step. I do intend to give partial credit. So if you're in that situation, that then just add a trivial definition for the things that you didn't get done. Just return an empty list or whatever makes sense, and then resubmit it. So when you resubmit, I will just we'll have a look at the diff, and if the diff is shows that you didn't completely restructure your solution or something, then I'll just regrade it and give you more points. So I realize it's a bit of a hassle for you to have to submit it twice, but it is much more efficient for the grader. That way I can give the grader simple instructions, and otherwise he's just not going to get through. So bear with me. Just try to do it reasonably quickly. It's not so much fun for me if I get a message 8 weeks from now that says, remember homework 2? So, you know what I mean. All right. Let's go and do the rest of this here together so that we have a record of it. So first of all, we're supposed to make a main object, and I like to, whenever I do a project, I like to just start afresh by just using SBT, because that way I know it's guaranteed to have the right structure. Now, of course, I can't remember what that structure is or how to make it, but I do remember that I wrote it down in homework 3. So here is the homework 3 description. So it says change to the right directory, which I did. Then just do this mumbo jumbo. Except here it says homework 3, so I have to now change that to lab 7. Now we'll go to lab 7. Now this line here, the only significance is so that it's not called hello. But hey, why not? So we're going to change hello to lab 7. And the remaining 3, they're always the same, so I can just copy and paste them. So now the SBT Eclipse makes an Eclipse project. If you use IDEA, you can skip that step and just load the SBT project into IDEA. But that way, you don't have whatever weird project IDEA builds from scratch, which I'm not sure how good it is. We have control, right? And as Lenin said, trust is good, control is better. All right, so.
Are you sure you want to be coding Lenin?
I'm not saying I agree with everything, but that one seems on the nose. So, lab 7. Here it comes. So, a new Scala object. We call it main. It extends app. All right, so now let's copy and paste what we need. We need the definitions of the 3 classes here. And I put them outside. Then I have this object here. So I put that inside main. Well, my expression Now I have an eval method here. That method has to go into some class, and I'll just put it on some object. I'll just put it inside main. And at this point, I should be able to print out what happens if I eval my expression. It needs a map for the symbols, so I have a map where x gets mapped to 5. Okay. No, I'm missing a parenthesis. Now let's run this as a Scala application. Contains build errors. Alright, well, I'm just going to continue it. Okay, now I'm in the situation that I always find myself with these IDEs.
Eval is only taking in one argument, and map should be.
Oh, thank you. Thank you. Yes. Yeah. So I guess I could, maybe if I moused over this, I would find this. Yeah. So, but just to show when I got confused in the IDE, which I regularly do, then I tab back into the terminal window, and I just type sbt run, because there's a good chance that I get a clearer error message that way. I just wanted to pass that tip on. So if you ever get confused by one, you can always do this in the command line. And so now, it's the same error message, but somehow this time I noticed it, whereas before it was buried. All right, so let's fix this up. So this goes in here. Okay, now why is it not working? Well, let's run it again. And now it says 23. Okay, so that's good. So I'm now moving on. I have this case class definition. Notice the definition does not extend expr, right? It's a different thing. So you have the expr class that has to do with expressions, and this definition sits somewhere else. We'll see on Wednesday how these definitions get parsed. Now I have a few of these here. So we'll paste all this into main. And now it complains that it doesn't know what this eval function is, so I have to define that. And I guess I have to start from scratch. So this is def eval, and it takes what? A definition. And a map that I again call symbols. And now it returns a new map that's take my symbols, and I augment it with some definition. And that definition takes whatever variable I defined in D, and that's called name. So d.name is mapped to, and then what the value of that is. So I have to now evaluate what this expression is. So that is eval of d.expression with symbols. Now I may have to put parentheses around here. Put this in a new line.
I just used the plus symbol. I don't know what plus equals.
Oh, I think you're right. Yes, because it. Yes.
It's not EJ.
Exactly. Okay. So now why doesn't it like eval here? See. It says overloaded method eval needs result type. Okay, if it needs a result type, I give it a result type. That's map of string int. And so we run it, and it does seem to produce the map that's expected. So we started with an empty map. The first definition sets x to 2. I didn't print that one. The second definition sets y to 2, y to x, and that's why x needs to be evaluated. And then I get the result here. So this is one of these things that I didn't do anything right. I just wrote the only code that made any sense.
Wait,
Any questions about this?
Wait, where's your
where's the next one?
with your definition class?
Yeah, where's all the case?
Okay,
Oh,
up
it's
here.
pop up. There we go.
Yeah. Yeah, so I put them all on the top outside main because I could. I figured this way it's more easily testable. It's still testable otherwise, right? But then the names get ugly. Remain.expression and so on. Yes?
Is it better to put it inside or outside? the case?
I think if you want to use them elsewhere, then it's better to put them outside.
It's functionally different if you do it.
The only difference is whether to the rest of the world they're known as xper or as main.xper.
I see.
And I feel these have nothing to do with main. Main is just there as like a unit test kind of thingy. Any other questions?
Oh, wait a minute. Okay, so I think I'm just having an aha moment. So you're treating the definition of a variable as an expression.
As it's not really an expression, but it's a syntactical thing.
Right.
And so it's not an expression because an expression has a value, and a variable definition doesn't have a value. So it's just a different thing. That's why you notice that all of these three classes here, they extend expression, but the definition class does not extend expression. And so it's structurally a different thing, right? A definition is something that makes me a new symbol table, that augments my symbol table. An expression is something that I can evaluate.
But the thing that I think I was tripping up on is why you're calling it value on it or eval. Sorry.
Why do we?
Oh, why I called both of those eval?
Yeah.
You know, I didn't have to do that.
Okay, see that was.
Okay. Well, hey, if it made you think, then that was a good choice of terms.
Kind of makes sense.
Yeah. All right, so that's that. You will be doing something similar to this, but slightly different in the homework. As with all these homeworks, you know, it's a little. One of the parts of the assignment is to differentiate between the notation that I use in the lab versus the one in the homework, so just keep those straight. So I have recorded this little tidbit, and I'll put it on the video. Hopefully it'll come out. And so I'll generally try to be on top with that so that you can use the videos for the homework. Any code that I give you this way, you do not have to attribute to me. All right. Start the homework early. That way you have a peaceful weekend. And any questions, as always, on Piazza. I'll see you Wednesday.